Okay, this problem is fairly straightforward, and most of it actually relies upon your ability to determine each H as being one of a diastereotopic pair, one of a homotopic pair, or one of an enantiotopic pair. So let's go through that. I will put up another video going through briefly what makes something each one of those things, and kind of like a back explanation of why and if we are concerned about all this. So, first compound. We've got these two H's here. So we are concerned about whether or not they are going to be diastereotopic, homotopic, enantiotopic. How do we determine that? We look for a stereocenter. This molecule has one. So, that means that these two H's are diastereotopic. Which means in brief that if you replaced one of them with something else, your resulting pair of compounds would be diastereomers. More on that in the other video. So, because they're diastereotopic, they are non-equivalent and will couple to each other. Which means that this guy makes this hydrogen show up as a doublet. These three will make it show up as a quartet, and this one will make it show up as a doublet. So overall, this guy's going to be a doublet of a quartet. Moving over to our second compound. We no longer have to worry about another H on the same carbon. What we have to worry about is this constitutionally symmetric hydrogen. What's going to influence this is whether our molecule here is chiral or whether it is achiral. How do we determine that? You can go through and look for plane of symmetry, point of symmetry, that sort of thing. I find it is a bit more foolproof to go through and just assign R and S to things, which is, of course, your favorite thing, but you do it a lot and it just kind of will flow naturally, and you learn the shortcuts to it. So, this stereocenter here, first priority is obviously the bromine, fourth priority is obviously the hydrogen. This carbon has more things on it than this carbon, so we've got second and third priority. So, he's going R, the fourth is in the back, which means it is what it looks like. He is R. This one. You'll notice that it has all exactly the same substituents on it. So, you don't even have to worry about what's going to be 1, 2, 3, 4. You just copy what you did over here. 1, 2, 3, 4. He's going R, and our 4 is in the back, so he is what he looks like. He is R. So what does this mean? That means that this compound is chiral. Because one of the hallmarks of a meso compound, an achiral compound with stereocenters, is that one center will be R and one will be S, mirrored across your plane or point of symmetry. This guy is chiral, which means that if we replaced this hydrogen with something else, say a D, so that we can keep our priority levels, what your resulting pair of compounds will be are identical. You replace this with a D, you still have RR. You replace this with a D, you still have RR. That means that these two hydrogens are homotopic and do not couple. Which means that the only thing that the circled hydrogen is coupling to is the CH3. Which means he's just going to be a quartet. Our structure up here, same sort of issue. And again, if you want, look for a plane of symmetry, look for a point of symmetry. In this case, because you've done this compound, which is an isomer, you don't even have to assign priorities. You can say, this stereocenter is exactly the same, has not changed, which means he has to still be R. And this stereocenter, all the same things, but you flip the BR and the H, which means it has to be S. This compound is achiral. What does this mean for us? So let's go through and replace the H's with D's again, so that we can keep our priorities and keep our RNS designation. We replace this guy with a D, he's still R, he's still S. Okay, cool. If we replace this guy with a D, he's still R, and he is still S. Okay, but what is the relationship between replacing this H versus replacing this H? Your compounds are now enantiomers, because if you replace this guy, then the compound with the D is R and the compound with the H is S. But if you replace this guy, the compound with the D is S, and the compound with the H is R, which means that they are enantiomers. Which means, of course, that our H's here are enantiotopic. However, this doesn't change terribly much because enantiotopic hydrogens don't couple either. They are, within the eyes of the HNMR system, identical. So, the only thing that we have to worry about coupling to is this guy, which is going to make him a Cortec.